Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
To introduce Mark Polyphys. It's his first visit to Microsoft Research. Mark graduated from the Catholic University of Leuven in 1999, and he joined UNC back in 2002, where he is currently associate professor at the Computer Science Department. Mark Polyphys is most famous for his structured motion work and his 3D modeling from images. He has done a lot of other work as well, like calibration and camera networks and real-time. So today he's going to be talking about camera calibration and shape reconstruction.
Okay, thank you. Okay, so obviously it's not just my work. Here are mostly the students, Sanjo Kim, Sudip Tusina, Shriram Tirthala, and Jingyu, as students, and then also a few colleagues and postdoc and a few colleagues I've worked with. So first, before kind of starting with the new results, I just wanted to show kind of the baseline where kind of started a few years ago, the stage at which we got with reconstruction from videos. So here what you see is an input video. This was recorded with a camcorder. And then from there, using search for motion, button adjustment, all the state-of-the-art techniques to do that, and select keyframes automatically, we basically get the motion and the calibration and everything from the camera, from the video sequence, and then beyond that, then do stereo and multi-view linking, etc., and get pretty accurate 3D models. We roughly got, we estimated that we have roughly 1 in 500 accuracy compared to the size of the object, both for the structural motion part from the button adjustment. So it's not really ground true, but it's from the button adjustment, from the residuals, we could estimate that, and for the stereo also from the uncertainties that we estimate in our process.
How long did it take to generate that?
That's roughly an hour or two of computation at the time, which is a few years ago. Probably be around half hour to an hour or so now. So where are we going with that now? So I won't talk a lot about this. Well, I won't really talk about this. I'll just mention it here. In that direction, we're trying to go now a lot faster, scale it up, and really address this particular problem here that DARPA asked us to look at. Is the Escape project. There's two different paths there. What we do is, there's a LiDAR-based technique. What we do is a video-based technique. So fully video-based, there'd be a number of cameras on each side of the vehicle, 4 cameras on each side to basically, mostly to get a wide field of view on each side of the vehicle. From there, we do structural motion to estimate the camera path, combine that with GPS, potentially INS. The vehicle that we'll use will actually have INS, but our goal is to be able to do without that. And basically geolocate our reconstructions. And the idea is to basically record for 6 hours. That's what they asked us to do. Be able to record data for 6 hours. You get to the base, you upload everything to, or you transfer disks actually to a cluster of 20 machines or so, and then in half the time it took to record everything, you reconstruct the whole city or whatever you've seen during that patrol. And the next day you kind of do the same and keep adding everything. What we want to, so this is work together with the University of Kentucky with Rugang Yang, and David Nister is the lead there in Kentucky. So we have a big team of people on both sides, and the idea is to leverage the real-time structural motion work that was done there, and then also the work that Rugang and me did on real-time stereo, GPU, put all those things together and try to achieve those goals.
So you're going to just use video, no range data at all?
No range data at all, but there is another part of the project which is based on what they did at Berkeley. So which is based on using the QuantaPoint laser scanners, which are very high performance laser scanners that rotate, that take lines at 3000 RPM. and combine that then with, have the software then from Berkeley that is now in UrbanScan, which is a small company that just started up, that is also working on this project. And they'll be then doing a LiDAR-based approach. And so both approaches will both mostly be complementary, since the LiDAR-based approach is a relatively heavy approach where you need a lot of hardware on the vehicle to do it, so they'd have like 1 or 2 scanning vehicles or so. But then every Humvee would have cameras. Eventually, in a few years down the road, there'd be cameras on every Humvee, and they'd record that anyway. And so they hope to be able to just leverage that to get models and have soldiers then be able to explore the city before they actually would be there or so, and just train and do things like that. Okay, so the different results I talk about a little more in detail today are those here. So we start with photometric calibration, then also talk about, so basically beyond the normal simple calibration, assuming everything is static with the camera, and we have a simple normal camera. So we go to photometric calibration now, including vignetting, etc. And then also to much wider field of view cameras, omnidirectional cameras. Then some other thing we looked at is what happens if, for example, with facades or so, most of your data is going to be on a single plane, and that can cause problems, can confuse RANSAC. So if your data is quasi-degenerate, RANSAC gets confused there. And so we'll talk a little bit about that. And then we go to shape reconstruction. One is combine silhouette and photoconsistency information. Try to do that in an optimal way. And then also look at articulated structural motion using a factorization-based approach to be able to reconstruct a complex body like a person or so by tracking features and looking at all the subspace properties of the motion subspaces. Okay, so the motivation for starting this work was when took a video sequence like this just without doing anything to the camera, without fixing things. The camera would typically adapt to the environment. Here we had a lot more light on this side of the scene than on this side. And so the camera basically got darker here, and if you just do the model, it doesn't look very good. So this is just running the video through our pipeline. So what we wanted is something like this where we correct. It's not perfectly corrected, but that's mostly due to saturation and highlights, which of course highlights are not dealt with if you compensate if you do radiometric calibration. And then here another example, again a moving video camera. Basically what you can see is that we start in a shadow region, and so the camera really gets a lot more light in here. But then here, as we go towards having a lot more direct sunlight here, then this basically corresponds to the same amount of light as here. And so we want to normalize for that, or basically we want to build up a high dynamic range video. Now I didn't do the tone mapping and so on, but this shows you the two extremes, normalize it towards one or the other. What we really have is high dynamic range, but didn't show that on this type of screen. The way we do it, since compared to other work, we want to be robust. We want to be able to deal with a moving camera, which means that the correspondences now are not parametric. So basically it's not a panorama where we can have a parametric model of correspondences. And on top of that, even if we would get, if our stereo would be perfect and we'd get all our perfect correspondences, even then, because of, for non-Lambertian scenes, if you look at it from different viewpoints, you won't even have the same value, the same amount of light coming. So assuming that there's a good part of the scene that is Lambertian, but that some parts are not, you do need a robust approach that would deal with that. And so you certainly don't want every point, in here this is a histogram, a joint histogram between the red channel in one image and the red channel in another image. And for every correspondence, we put a dot here. And so what you see is, of course, that we have a transfer here, a transfer curve around here with some noise around it. But then beyond that, we have lots of points all over the place, which are due to highlights or in one image or the other, and just mismatches. And so if you just, like most approaches, basically just take for every point, write out a linear equation, and then just do least squares, and this wouldn't work. So what we do is we use dynamic programming to just find here the most likely transfer curve, and then use that weighted by the amount of support. Every point on this curve is weighted by the amount of support it gets. So if there's a region where there's no data at all, the curve will just be straight, the shortest path. But then we don't use that because there's no data to support actually that path. So that way we can actually have a very robust estimate very, very robustly the transfer from one image to the other. Once we have that, we basically use those equations with the AMOR model that Columbia proposed. Sri Nayar and co-workers, they had this. They've built up this model from 200 real cameras. They estimated, and they have a PCA basis for the response curves. And this is an example of a few of the main components in log space, because we want, in our case, we need to work in log space because we still also have an unknown exposure. We want to be able to deal with unknown exposure because that's a multiplier. We want it to work in log space so that it's just an additive term.
Yeah, but that doesn't guarantee monotonicity, right?
No, it doesn't. That's right. But it's, I mean, we don't get non-monotonic curves. So we've very recently done that to deal with vignetting. Again, our goal is, while we haven't completely shown that yet at this point, but our goal is here also to be able to also work with moving cameras. And so we wanted to remain robust at all stages in the computation. So the trick we use, so basically what we want to do is that every equation we use, we don't want to use any equation that only comes from a single pixel, from a single correspondence, or from a, we only want to use data that is supported by a lot of other data. So only consensus data we want to use. So for doing that, it means that if for dealing both with so we had already our approach here, dynamic programming approach, to be robust for all for everything but vignetting. If we add vignetting in there, then then suddenly those vignetting terms also come in here, and we can't do that immediately. So what we figured out is that there's actually a few points. If you have, our assumption is that you have constant vignetting, which is the assumption that Dan Goldman used at UW. And it's actually his data here. So if we have constant vignetting in all the images, then basically at a point that is equally far from the center of vignetting, which we assume to be the center of the image, in that case, if we have a point here, the center of the optical axis here in the panorama for one image, and here for the other one, then any point at equal distance between them will basically have the same amount of vignetting. Unknown vignetting, but the same amount. So basically, that effect cancels out, and what you have is the vignetting will cause a reduction of light, but the same reduction on both sides. And after vignetting, you still have the same amount of light coming from both cameras. And the only difference is going to be caused by exposure changes and things like that, and white balance, etc. So basically what we do now is our previous approach, but we only apply it to a small band around the parts that are equally distanced between pairs of images. And so we can do that for all the pairs. So of course one pair doesn't give them that much data. But if we have a whole panorama, every time we have overlap, we can take this in between band. And so we actually do get a lot of data. Of course, here it's very important that there will be regions with no information. It's important to do the weighting and only use parts that actually have support. But that works well. We get very good results at this level. And then once we've compensated for exposure and everything, then of course it's very easy then to estimate the vignetting, because all the other effects have been taken care of. The way we do it to be robust here is we look for, so basically we should have the same amount of attenuation or relative ratio of intensities for a certain radius, combination of radii in the image. Of course here there's, if same radius, we assumed we have no change. So it should be a ratio of 1 in intensities. But at other places, the vignetting will cause some ratio. So basically what we do is for every point in this, we kind of discrete this space. And for every point, we take we add up all the, well, we keep track of all the values, and we keep track of the median value for that, which again is going to be then, and again we weight them according to how many values are here in this. And so again, we get a robust approach there. And so that way, by doing 2 steps and separating things, we can actually do this in a robust way. And here's some examples. That's the original images, of course, a big RMS error. These are the results of Goldman and Chen. They have a residual RMS error of 10, and so we get a residual RMS error of 8. while having a much simpler approach. It's a completely direct approach, right? This was a nonlinear minimization approach. So it seems to work quite well. Because, well, actually, you can get some idea. Now I show with blending. So I alternate with and without blending here. And what you see, the images are not exactly placed at the same place, but still you see that there is actually some residual misalignment. You see things kind of move a bit non-rigidly, and that's because there's some residual misalignment, which in the blending actually, once you blend things, other images come up on top instead of, and that actually shows, so that residual misalignment causes, especially all the high gradient areas. Well, actually what we do is get rid of, we don't use high gradient areas for computations in the first place because those are unusable. But even for other places, there's actually misalignments. And that's where a non-robust approach, even here, will actually have trouble. And I think that's what explains this difference here, is that we're robust, and so we kind of get most of the points properly, while this will kind of, for some of the outliers here, will kind of be drawn towards those outliers, while we are not. That's my explanation, but we have no way to exactly verify that, but that's what I think is the explanation. Another example here, where basically this is the result after both blending and correcting with our approach. And I don't think you can really see any seams anymore in the approach there. We're also interested in using those kind of cameras here for very high resolution panoramas, for building up backgrounds and things like that, for being able to capture. My final goal is here really to be able to capture something happening anywhere in this space, have cameras in different locations, a camera network that would be able to reconstruct activities anywhere in this space. The first thing is, of course, to kind of model the own space of each camera separately, build up a big panorama, and there, of course, again, we can use all those all this calibration to also compensate for all the things. Okay, so, well, let me skip that for sake of time. One thing maybe is that also compared, we didn't have data to compare with Litvinov and Chechnev's approach, which is also very relevant to this, of course. But given that they have nothing to be robust, they're very general. It's a very nice approach. It's completely linear. But they also have nothing to be robust. And there's no direct way to make it robust because they estimate all parameters at once. And so there's no 2 points having exactly the same set of data observations typically because you have a high dimensional space that you look at. So the next thing is omnidirectional camera calibration. Here what we did is use the concepts of, so this is very related also to what Singbing is doing, or has been doing with Richard. It's using the concept of multi-view geometry to look at omnidirectional cameras. So typically, just as a refresher for that, so for a normal perspective camera, we really have two linear constraints per point. Basically, what we say is, given this camera image here and a feature point here, the real feature, the 3D point that corresponds to this must be somewhere on the back projection of the row and the column, or the other way around. So the row and column. So that gives us two constraints per feature. So we have, basically we can back project. And so any combination now with multiple images, any combination of 3 of those constraints, you don't need to use both from the same image here, of 3 of those constraints will actually allow you to locate a point. As you add in a fourth constraint, you actually, you can't just take random values now, because they won't correspond. So if you know that 4 things will correspond, this actually starts telling you something about your camera configuration. And so the nice thing is, since all these projection operations and all those things are all, this coincidence property is also is basically a determinant, and that's multilinear. So basically, we get all multilinear constraints, which are known as the epipolar, trifocal, quadrifocal constraints. It doesn't go beyond that because we're 3D space plus 1 for the, the redundancy, and so that's 4. That's it. So the idea is, well, if we have a known center of radial distortion here, some people make other assumptions, but we assume it's just known, and it does work pretty well. And at least in the first stage, it's a good approximation. And then after that, you can do a nonlinear refinement, a Bannon adjustment or so to get beyond that. So basically, if you know the center of radial distortion, then the only thing that radial distortion will do is move the point here somewhere back and forth along this line here, depending on the distortion. So what we decided to do is just forget completely about trying to use the information about where this point is along this line in a first stage. We're just going to assume that we don't know anything. The only thing we know is that it's somewhere, it should be along this line. And so what we know is that we have this one plane back projected. Instead of two constraints, here in omnidirectional case, we have one constraint only. And really what we have is a 1D camera where we basically, we have a feature projects now on one of those lines here, this 1D bundle of lines. And so if you write that out, the same way as the normal quadrifocal constraints, you get here a quadrifocal tensor. Now, because those are only now a 1D set of lines, it's only going to be a 2 by 2 by 2 by 2 tensor instead of a 3 by 3 by 3 by 3, etc. So it's 16 coefficients instead of 81. And if you do the math, the constraint counting, then you would see that there's, so you need 15 equations to compute it linearly. There's only 2 internal constraints. One normal quadrifocal tensor has 51 internal constraints out of 81, which means it's almost impossible to compute it linearly. This one actually makes sense to compute linearly because we only ignore 2 constraints. Roughly the same ratio as the fundamental matrix where you have 1 out of 8 constraints that you ignore. And so the approach is you compute this tensor, so you need 15 points in 4 images, which is a lot, admittedly. But so given that we can compute this tensor linearly, then we can use the known approaches. For example, Richard has a paper on how to do that, to reconstruct the scene based on that, projectively. And then once we have reconstructed our scene, then we have a 3D model of the world. And then we can use that 3D model as a calibration pattern for our camera, and actually for 4 cameras. So we don't even need to calibrate the same camera. We could calibrate 4 cameras at the same time, potentially. And we did that synthetically. But in practice, it's actually relatively hard to use this approach here because there's several degenerate cases, and one in particular here, which is when 3 cameras, the optical axis of 3 cameras will intersect, which, for example, is the case if you do pure rotation, would also be the case if you just take pictures from 3 different sides looking at an object. In that case, this tensor gets degenerate, and actually, but as often in these kind of cases, what you get is a simpler. So often when you have a degenerate case, associated with that, there's also a simpler algorithm for the simple case. So for example, if you do pure rotation, you get a trifocal tensor now, because basically, if you do pure rotation, really you're looking at a 2D world, right? Your panorama. That's what you're looking at. And so now we have a 2D world, so we only need 3 constraints, 3 images to over-constrain our system. We get a trifocal tensor here. So this trifocal tensor was used in another context before. I think the first use was Longquan and Kanade. You get a 2 by 2 by 2 tensor. The nice thing here, no internal constraints at all. So 7 points here are sufficient to compute it 7 points in 3 views, which is a lot more reasonable to obtain automatically, especially for pure rotation, for panoramas, SIFT and so on, and other feature detectors would do a great job on that, typically. So what we do is, again, same strategy. We reconstruct our 2D panorama independently of radial distortion. Once we've done that, then we use the panorama for calibration. The nice thing is actually using self-calibration, so that our rows and columns are orthogonal, and that our aspect ratio is constant, for example, in the images. That is sufficient to get a metric reconstruction, so to upgrade our initial projective reconstruction to a metric one. Now, a metric reconstruction of a 2D panorama of basically the plane and infinity means that you really now have, for every 2 rays, you basically can immediately measure the angle because it's a metric reconstruction. So you have this ray, which is, for example, the optical axis, and then this ray, which is an outgoing ray that you have reconstructed. Well, that basically, it tells you it's this many degrees. That's what a metric reconstruction of the panorama. Oops. Back. Ooh, that was scary. So
the aspect ratio is not 1 within the problem.
No, in this case, we can compute a constant aspect ratio also. And at this point, we don't assume any symmetry at this point or anything like that. Then beyond that, so basically here an example. We can use that for different types of cameras. So for example, here, just 3 pictures taken with a fisheye lens. So this is a full fisheye lens, 180 degrees. We extracted SIF features, matched them automatically, had a RANSAC process to compute the trifocal length. So it's all automatic, basically. And what we get is this here, all our measurements. And as you can see, it's quite accurate. I think if just looking at the plot, it might have a smaller band than some of the results I've seen from using Bing. I'm not sure exactly. Just at the width here of this band. So basically, it is really what you would expect for a fisheye integration. This is the normalized radius, so up to the border of, up to this distance here. And so what you see is a roughly linear behavior in degrees, which is what a fisheye model actually aims to achieve. So that seems to make a lot of sense. Nothing of this was imposed, and every point you see here is measured independently from a reconstruction kind of back projected in one image. So the colors R, G, and B have to do with points reconstructed in the 3 different images. Same thing here for a cata-dioptric system. So here in this case, again, automatic matching, 3 images like this. And in this case, we actually use the center of this circle. So that's the only non-automatic step here. And start with that. And then what you see here is, of course, this camera here has basically a viewing angle, something like that. So from -50 to +50 around the horizon. And of course, we don't even cover, or features don't cover that whole range here. And so indeed, you see, we now directly, exactly the same algorithm. We don't need to change a line in the algorithm. We'll now compute properly around 90 degrees features, above and below the horizon here in this case. And so that's also fully automatic, except for the center of the circle there. Okay, and so the nice thing is actually, because it's the same constraints as in the multi-view geometry stuff, we can actually also do mixed tensors, which combine perspective cameras with 2 constraints per camera and 1D cameras, omnidirectional cameras. It just all flows out of this. Something I won't talk about, but just mention, is that for calibrating networks of cameras, we have a way to do that just from silhouettes. Here we use somebody else's data, Peter Sand's data from a SIGGRAPH paper. He has 4 minutes of 4 videos which were actually unsynchronized. So there's a subframe difference and several frames of difference also. And so we can both compute automatically the temporal offset to a subframe level, roughly a third of a frame, which is a hundredth of a second accuracy, and also very precisely the camera locations. We verify that by looking at a reprojection of the visual hull and see that we indeed fill up the whole silhouette. If calibration would be inconsistent, this wouldn't happen. And there's only a few errors around the fast-moving body parts, which is because of the subframe temporal offset, which was not compensated here. Okay, so on to the next thing. Another project we've done, so something I've done with Jan Michael Fram, who was here, I think, at some point. So he's now working on the Urbanscape project with me as a postdoc. And so the thing we looked at is the problem when you have most of your data is in a plane, which is the general configuration for many estimation problems, so for the fundamental matrix, but also for estimation of pose, etc. Then, for example, here, 337 matches from this scene here, this tray plus chandelier, 337 matches in the plane, and then only 11 matches of the plane. And so if you just throw RANSAC at this, RANSAC will very quickly find a solution that includes all the inliers here on the plane, and we'll say, wow, this is a great solution. I have 90% inliers, or whatever the number would be, and it will just stop. And most likely, it will not have included any of those, and you'd get an incorrect solution. So here we actually computed the likelihood of that happening. Let's say we have 90% inliers total. Of this, we have 85% or 88%, well, not of that, but of the total, being in the plane. In that case, the likelihood of getting a non-degenerate sample, which is what you initialize your RANSAC from, so getting more than 6 points in the plane, basically, not in the, getting 2 points not in the plane, sorry. So the likelihood of getting at least 2 points not in the plane for F and other similar scenarios for projection matrix estimation or 3D homography estimation is 3%, 2%, etc. And so the likelihood that RANSAC will actually stop with a correct solution that has included some of the outliers there, just the likelihood of having at some point had a good sample at least, is going to be 36%, 19, 54%. So it's really most likely RANSAC, and it's even a lot worse here if there's this much percentage of points like we have in this case. We're closer to this scenario here. And so there's only a very small chance that RANSAC will actually just end up with the right solution. So for quasi-degenerate data, it's a big problem. RANSAC is a big problem. Notice also that model selection, the Thor's approach for model selection will not help this. It will just say, well, it's a plane. And that's the only thing it will say. It will never figure out that those points are not even in the mix at the point that the model selection is deciding about a plane or a fundamental matrix. Actually, even if you put those points in there, the model selection will still say it's a plane. Because model selection, typically, as it is used, will select between a homography model and a fundamental matrix model. Now, even if those points are correct, there's so few of them that it's so expensive for the model selection to upgrade all those points from planar points to general 3D points. So the price you would pay to have those be general points is a lot more than the better fit for those points here to the fundamental matrix model. So if you basically do model selection, even including those points here, model selection, the standard way, because you only have purely planar or purely general 3D points, the cost for the purely general 3D points is a lot higher when you have most of your points being exactly in a plane. So what you need is like an in-between model, which is part of the points in the plane and then some out of the plane. That if you had that in your model selection, you might actually get it, but you still first need your RANSAC to actually find those points. So model selection doesn't solve anything there. There was another approach at CVPR this year by Schum et al. Actually, I'll compare to that in a moment and say a few words about it. Quickly, how our approach works. So their approach is called DegenSAC, and so we had to find something else. So we call it QDegSAC, whatever. The approach really consists of first doing a normal RANSAC, whatever. Most likely, we won't include the proper inliers here, as we've seen on the previous slide. But then from there on, we try to find a model to see if in our data, if somehow we can find a smaller model. So basically, from the fundamental matrix, which will correspond, if you do it linearly, to a data matrix of rank 8, we try to see, is it possible to fit all our rows here in a data matrix or many of those in a data matrix of rank 7 or rank 6 or rank 5, etc. And so we go down, basically, up to the moment that our number of inliers drops. So what it means is if having a lower rank data matrix means having a larger null space. So what we do is we span vectors in a null space. And so normally we have one vector for the null space, which corresponds to the 9th singular value, basically, if you do the data matrix. Now, if we want 7 here, instead of 8, 7, then we basically have 2 vectors now spanning our null space. We have a theorem that proves that just estimating for every point, estimating if it's an inlier to the fundamental matrices by those 2 vectors here, spanning our 2D null space, is sufficient to strictly bound the algebraic error for all possible fundamental matrices in this whole 2D null space. I can't really go into detail there for sake of time, but so we have a theorem that proves that. So we start from 8 here. That's the number of inliers. If we try to fit it robustly to a rank 7 matrix here, in some sense, then basically we get almost the same amount of inliers, which means that most likely our data really only spans a 7D space, not an 8D space. Actually, really a 6D space, because we still only lose a very few inliers there. If we try to fit it in a 5D space, a rank 5 data matrix, suddenly we drop to below 20% of the original amount of inliers. And so systematically in all the experiments we did, there's always this huge gap here. You put a threshold anywhere between 80 and 20%, it always works. So for some practical reasons, because we kind of need to keep checking until we give up in the end, it's better to put it higher than lower, because RANSAC will just give up earlier and say, okay, this is the real rank here. Being able to kind of find 20% inliers in RANSAC is an expensive thing to do. So practically, it's better to have a higher than lower cutoff there. Once we've done that, of course, then what we do is Once we know this is our real rank here, then we go back to the data, to all the outliers here that are, if the total number of potential matches was this high, then we go back to that, and then we try to look for points that will complement our data matrix and augment the rank in a meaningful way. And so we look for the 2 additional points we're missing in this case. But it's completely general. If we miss 3 additional points, we'll get 3 points. If we miss 5 additional, it's just a general thing. So here's our example. That's what you typically get if you don't do the thing properly. That's what we get. So that was this result that I just showed. Here you see which features in the end. So those are the out-of-plane features, all 11 of them. If we did 100 trials, how many times all those features were actually included in the final, final selection here. And so you see that it's 8 features are included every 100 times, and all the other ones are included at least 85% of the time or so. So really, it's very reliable, and every single time, we get the correct fundamental matrix out of it. While the normal RANSAC only gets it in 20 or 30% of the cases, does get the correct solution. Comparing it to using the data of Chum et al., their approach is, instead of doing it after the fact, once they have a solution, try to see if it's actually a degenerate one. What they do is every time they take a sample, a successful sample that seems to have a lot of inliers, they actually check the sample for degeneracy. It's an alternative approach, but it means that you need, for using their approach, it's potentially very efficient, but you do need to have a specific test to detect the degeneracy in a sample, which is not completely trivial, and you need a separate test for every degeneracy you might actually encounter. So you also need to really be aware of all the degeneracies and explicitly test for them. Well, in our case, we don't need to know anything about all possible degeneracies. It just automatically kind of works its way through all possible cases. As long as we have linear equations to work with, we can do it. And so here the comparison, basically both really compare very well. So our algorithm here maybe has margin a few % less inliers, but in the end, most of them, 25 out of 35 here, are basically always included, and that's plenty to always get the correct solution here. And again, they had a very nice data set, it seems, for showing their point, because RANSAC only gets the points in 10% of the cases.
Mark, so you find a fundamental matrix, right? And you find basically the family of fundamental matrices that.
Yes. So we find the whole family. That's indeed right.
And then you go and find all of the points that agree with that family of fundamental matrices.
Right. And we have a theorem that just doing if it's a 2-dimensional set, then we only need to do 2 checks, and not, of course, exhaustively sample all possible fundamental matrices in that space.
Right. And so then, what is the next step to get the actual fundamental matrix out?
Well, so we keep doing that. So we keep kind of getting lower, kind of going to smaller and smaller rank matrix. Once we are here and we know that, because of this drop here, we know that this is the real rank here, then we basically, in the outliers, so all the points, so we have all those points are inliers, and basically span this 6D space. So we take what we do at this point is basically do closest rank 6 approximation of that data matrix for all those inliers. And then among all the outliers, we do a 2-point sample, because we need 2 additional points here. In this case, because we have 1 equation per point, we need 2 additional points. So basically, we do a 2-point RANSAC, where every time we take those 2 points, that's 2 linear equations, we add that to our rank 6 data matrix we have, or closest rank 6 approximation. We add that together, that's a potential sample. And we see among the outliers, we know that all those points are inliers. That's a given. But then among the outliers, we actually check how many of them are inliers to that, support that hypothesis. So basically, in the subset of the points that are not in the plane, we're looking for additional inliers explicitly. And so we look for a consistent support in that. And that means that we can, because now we're explicitly looking for those points, we can even deal with, if there's only 1% of the total, if there's only 1% of the total actually out of the plane that are consistent out of the plane inliers, then we can actually find those in an efficient way.
So the ones that you're finding, are they consistent with a single matrix? Or
Yes.
They're just
Yes. No, they're consistent with a single fundamental matrix. No, with 1. No, because there's only 1 correct one, right? So they're going to be consistent with 1. So we take 2 points, we add them to our rank 6 matrix. That generates 1 hypothesis. And we check for that one if it's consistent. And of course, the nice thing about our approach, which others weren't doing, is we can trivially use it on other type of data. here, pose estimation. We use the same data. We had 3 images of this. And then here, if all the points are in a plane, then instead of having a rank 11 matrix, it kind of goes down to a rank 8 matrix. Again, we didn't kind of need to compute what the rank was going to be or whatever. This just happens. And so from here, we kind of then are able to include this many additional inliers out of the plane. Right, and so here again, same kind of behavior. The standard RANSAC fails in many cases there. We did the same we have the same behavior for 3D homographies. We also actually looked at the degenerate quadrics. 2 planes form a quadric, and if most of your points are on 1 plane, then it's the same thing. So we looked at different things there. Well, I already explained all of this during the presentation. So next thing we looked at is now we're on shape reconstruction instead of calibration problems. We're search for motion calibration problems. We're on shape reconstruction. We looked at combining photoconsistency and silhouette information. Those are really complementary information. Photoconsistency typically you'd kind of use somewhere in the middle, at more or less frontally facing surfaces. That's where you actually get good data for checking out photoconsistency. Silhouette information is really at the tangency. Now theoretically, and I had that discussion with Singbing, you could basically, so that's like photoconsistency kind of race you would use, and then this would be the one you'd use for the silhouette. Theoretically, all of this can just be put together in one photoconsistent model, but in that case, you need to have a photoconsistency that can really model variations in non-Lambertian surfaces, etc., going over 180 degrees, like the whole hemisphere, and have a photoconsistency model that can actually deal with that. While it's much easier to only have to deal with a small angle here and use separately the very strong information that you get at silhouettes. So in many cases, lots of people are actually using those two type of information separately and explicitly, beyond photoconsistency, explicitly impose silhouette constraints. Now, what people typically do is just throw those 2 types of constraints in a big energy minimization framework, and so they try to get close to have a surface that they evolve, keep it close to the surface somewhere, close to the silhouettes. They have forces pulling it back to the silhouette, and they enforce photoconsistency. The problem with that is that by having this force to try to keep things close to the surface, so that when you have ambiguities in your photoconsistency, then that you try to keep at least close to where you know you have a tangency to your visual hull, that those forces, even with perfect data, would always create a bias. So things that are close to the silhouette will actually be drawn to the silhouette. And so the way that people have implemented this, there's always this bias to the silhouette, to the visual hull, if there's a force basically drawing the surface to the visual hull. And so at the right place, that's good, but at other places, it will actually bias the surface slightly towards the visual hull. So that's why we wanted to find an approach that would not have that behavior. Also, if you have small perturbations in silhouettes, you're not going to have any catastrophes. If you have small perturbation in calibration or in anything else, you could actually have, or if you have ambiguities, you could have big problems with photoconsistency. Photoconsistency could just completely fail. And so photoconsistency, typically, you always need to have a trade-off with a shape prior. So you always need regularization when you use photoconsistency. So what we try to do is to have an approach that will trade off photoconsistency and shape priors, as we think we should, but enforce exactly our silhouette constraints. And the nice thing about enforcing it exactly as a strict constraint is that we don't cause any bias towards the silhouette. We just enforce the silhouette constraint, and that's it. And there's no further forces pulling things towards the silhouette. So here's a 2D example, a synthetic example. What we do is, let's say here we have a very simple case here. So we just have 2 views, let's say, or let's say 4 symmetric views or so. This is our real, this would be our object, the 4 lines here from the visual hull. And so those are here the nodes of the visual hull. And so what we'll do is we'll try to compute every segment here separately. So basically what we want is a curve that will kind of connect the edge V1, V2 to the edge V2, V3. So we know we have to be tangent here somewhere. And then that some be connected here, etc. And so for every segment, we'll kind of set up. So basically, in this case, it would be for a segment with this and this boundaries here, we'd set up a graph here, which we'll use afterwards for graph cut, a graph filling it up with photoconsistency values and potentially some values for taking the shape prior into account, so for preferring shorter paths. And so that will just describe that segment. And then what we do is, well, we can do that for every segment. Notice that there is overlap between them, so they share, every time they share one edge here in the visual hull here, they always share one. So we can do that. Basically, we can do the whole thing here. Every segment, all link them together, and then we'll do one big graph cut instead of all separate graph cuts. And in that way, by linking here, so that all the points, all the nodes here in our graph are the same nodes as those ones here. So you see V2 and V2 here. So those are the same nodes, and so we want those to be consistent. And so our graph cut here, is also here. And so the problem is, if let's say we take a source here, and then the back here as a sink, if we want to do the same here, then we have a source here, and this as a sink. But then this was a source, and now here we have it as a sink, but it should be the same point, so we can't do that. So what we do is actually alternate. So what we have is source and sink, and then here we'll have sink and source. So now this node is a sink here and a sink here, or a source here and a source here, and this node is a sink here and a sink here, and so on. So if we alternate, as long as we basically can remain consistent here in our graph, and so basically that allows us to link this curve to exactly this curve, so that we have exactly the same tangency point here and here, which is basically what we need to have a continuous curve, that continuous solution like that. If we can link all the way around, then we'll have a watertight surface. We'll always have a watertight surface coming out of this graph cut, which exactly satisfies the silhouette constraint. And then we do a min cut, and we get basically what we want. And so to be able to do that, we need an even number of faces here. That's the important thing, to be able to kind of close consistently. Now, the nice thing is in 2D, it's relatively easy to see that it's always like that. Now, of course, what we're really interested in is 3D. The nice thing is that it's easy to show also that this is also always possible in 3D. So what we have here is, to be able to do this thing consistently in 3D, what we need is this is an object, and this here is every time the silhouette generator. So this is where the tangency from one view cone here will happen at one of those lines here. What we need is that every time here we have, so basically we draw all those lines on the surface, and then that surface, that patchwork, we need to be able to have a 2 coloring of that patchwork. Now the nice thing is you can prove by induction that that's always achievable. Because let's say we have a solution for this level here, we add one more view, and everything behind, so everything on the front here that is facing towards the camera, we keep the color, and everything behind the camera, so past the contour generator, the rim here, we flip colors. And so like that, you can always guarantee that you can do a 2 coloring for this. And now what we do is basically, every time we have pink, we'll use the sink, and we have blue, we use the source, and we can flip that way. And so this one always, all the ones it has to connect to, always of a different color. So you can flip sinks and sources.
Why are you going to pass through another vertex?
I'm not sure what you mean here. So the camera is here.
Yeah.
Oh, if you collapse here, oh yeah, that's a non-generic case. No, but so in practice, no, that's not a problem. You always have in some sense, you could have an infinitely small thing. What it really means is that that we don't need to optimize there, that this is a point on the surface there. And so it's a known point then. If the triangle collapses, then this is an actual point on the surface. And so we don't need to compute anything and do a graph cut there at that point or so. We know it's a point on the surface because there's multiple tangents. So it's not a problem. It is, however, in practice, it is a problem. All those kind of cases, the non-generic cases, and due to discretization, they're actually a lot more likely than not, are actually, in terms of coding, they're kind of hard to deal with. And that's why we're still limited, actually, in terms of generic shapes. Here an example. Those are the rim mesh we computed there. And so here is one of the segments from this pear-shaped object. So one of the graphs, the subgraphs, few of them. Here's some synthetic example, well, one synthetic and one real example. Here, the original visual hull, and then this is our computation. The colors have to do with, again, which facet we were on. The yellow points are places where we don't have views really looking straight on top of this, and so our photoconsistency, we have no information of photoconsistency to actually go there. We don't have at least two views seeing those voxels, and so we just leave them on the surface. That is actually another problem, because this happens when you have a very small segment here. And so it means that you have somewhere tangency here and somewhere there, and so it's typically in places where you have many tangencies very close together. That's where you don't have cameras kind of looking at them that can look inside. And that's actually fine, because if you have tangency here and here and here, that's probably because the surface is really there, and it's unlikely that you have something like that happening. Here's some real results. But we have more work to do there. The data is from Esteban and Schmidt that did similar type of work in a big minimization framework. So really the further work here is in being able to deal with more complex objects, non-genus zero, and lots of things like that. Also, we had the coding up of the first part took so much time that we had a week left to do the photoconsistency and all of that, and we did a number of choices that weren't the most optimal ones. So the last thing I'll talk about is factorization of articulated shapes, potentially also including some non-rigid body parts. It's all based on the work, the factorization, earlier factorization work, Tomasi Kanade, where basically the key thing is we have a matrix here, rank 4 matrix representing the shape, and then another rank 4 matrix representing rotation and translation for every view. These are all assuming orthographic projection, so there's a 2 by 4 matrices here. And so you basically get, the product of this is basically all your feature tracks. And so you get a big matrix, which you know by construction should actually have been, if it's originating from this orthographic projection model, then you actually know that it should be rank 4. And so that's on what factorization is based. Building on top of that, there's been work on multi-body shape and motion factorization. Basically, if you have multiple bodies and they're truly independent motions, then because the shape are basically spanning orthogonal subspaces here, there's zeros, no interaction here. And if those are independent, then basically this thing will not mix, and you keep a rank 8 matrix, and there's methods to actually nicely find out which feature work with which, because they're in orthogonal subspaces. So the segmentation, motion segmentation is relatively easy in this case. There's also been work by lots of people, Bregler and Brandt and Kanade with Shao, etc. Been working on non-rigid shape factorization also, where basically what you do is now you have a number of key shapes, and the shape you observe is a linear combination of those key shapes. And so in that case, you can do some type of deformations. Typically, multi-body shape and motion factorization is, as I said, it's based on this. You can write down a shape interaction matrix, which will only have here a full block if this track if those two tracks, so you have all the tracks here and all the tracks there, a block is non-zero if the two tracks are in the same subspace, so on the same body. And so factorization is relatively easy, at least in practice, and there's robust ways to do that. Now the problem is that actually fails if you have non-independent motions. And clearly an articulated motion is not independent, because there's one point here that is both on this subspace and this subspace, right? On this shape and this shape. It's always shared. So it means that basically your motion subspace here is actually constrained, and you always have, so although there can be an arbitrary, so this is just one joint with one intersection, it means that the translation, without loss of generality, we can basically place decide that this point here is the origin, the joint is the origin, and then all the translations here and the translations here will be shared. And so you basically have 2 rows of your matrix with 8 columns. You have 2 of them that are the same. So clearly it's a rank 7 matrix instead of a rank 8. The problem is that those originally orthogonal subspaces, because this matrix is rank deficient, will actually start mixing. And so you can't do the simple trick anymore. Same with a hinge. You have an additional constraint. You have basically a 2D space now homogeneous space, so a 1D space, a line, so 2D space homogeneously, because there's also a constraint here. In one way, if we choose the rotation axis to be the z-axis, then on top of the common translation, we also have a common row here in the rotation matrix, and so we get to a rank 6 matrix. So that's the work we did, and actually at the same time, independently, Treseder and Reed did the same work. Both papers appeared at CVPR this year. So the nice thing is that you can, if you figure out that there is a rotation, a constraint there, an articulated constraint, you can enforce the lower rank to get rid of more noise. And actually, what it really gives you is that instead of having this body kind of float compared to this body, now they'll be forced to have an exact intersection and an exact joint. The nice thing is actually that the intersection of those subspaces actually exactly corresponds to the intersection of the motion subspaces corresponds to the motion subspace of the joint, which is after the fact is kind of an obvious thing. A nice thing we've worked on now is that this extends, all those constraints here extend to non-rigid body parts, which then will have, instead of a 4D, a large dimensional subspace here. But it also extends to that under the constraint that the sum of the mixing coefficients of the key shapes, that they sum to 1, which is actually a very meaningful constraint. People haven't been looking at this. Actually, what Xiao was doing with Kanade, the way that he was choosing his key shapes actually does enforce that constraint for the key shapes at least, because he gets 1 and then zeros. But I think this is a more general constraint that is actually a very useful one that people should look at. It's one that makes a lot of sense and would be there in many cases. It means that you don't actually use your parameters here to kind of scale something, but you just kind of mix in kind of barycentric way. You mix between different key shapes. So as long as that constraint is satisfied, then articulated points will be preserved, even if this is a non-rigid shape and this is a non-rigid shape. The articulation and rank deficiency, etc., will all be kind of preserved there, and the intersections corresponds to the correct articulations. So that's a new result that we hope to have published soon. Well, that's just to show that the shape interaction matrix does fill up, doesn't have this sparse structure anymore. This is after segmentation, reordering the matrix so that we have one body and the other body, and there's interaction now. So that should be zeros if they were independent. And so you see the object on the right that we actually used for that. That was our CVPR 2005 approach. Use scale T-tracks, enforce the rank constraint, do subspace clustering of intersecting subspaces. It's a non-trivial problem. We use GPCA for that. That can deal with intersecting subspaces, factorizing those by basically fitting polynomial terms to it. The problem of fitting polynomial terms is that it's okay for 2 subspaces, maybe 3, but beyond that your polynomials get so high order, you need so many tracks, and you ignore so many nonlinear constraints that it just completely starts failing. And then once we have that, we compute interaction, the articulation, so the intersection of the subspaces, and then we can recover the different parts separately and have them articulated, etc. Here, just quickly some examples of that to show you. So the articulation is just directly this intersection, what we compute, and you can see that it's really where we expect it to be. That's where the actual joint is. The actual rotation axis is located. Same for the hinge here, or the joint at the head. Some new work on shape factorization. So given that we wanted to be able to work with much than 2 or 3 shapes, we had to find something that worked better than GPCA, that was more general. There's an approach by Zelnik, Manor, and Irani, but still that also had problems. And so what our approach does is, let's say you have 2 subspaces here. You first normalize the points. It doesn't matter because they still stay in the same subspace. So we normalize them so that they're on a hypersphere now. So we only work with normalized vectors. And then we get one subspace, another subspace here. And we take points on it that are close together and fit a local subspace to it. And so instead of directly comparing one feature to another feature and look at the angle between them, what we do is first fit subspaces and then look at the principal angles between the subspaces. That seems to work very well to kind of cluster all those points and all those points together. There's sometimes some misregistration around this region here because you fit basically 2 points that are, your neighbors are actually on other subspaces. But you can recover that once you found then the subspaces, and it works pretty well. What we show here is that compared to the other approaches, our approach actually works significantly better. Gets almost no outliers there. The outliers are in terms of hand verification of the feature tracks. And notice, interestingly, for 6 subspaces here, Jingyu moving like this, we have 6 different subspaces that we were able to identify. GPCA just can't pull it off. There's just not enough data to even start computing anything. So GPCA is really limited in that sense. Beyond that, so once we factorized things, then we have all those subspaces. Now we're actually interested in how are those connected. And so that's also sent to some place. What we compute here is basically we are able to compute the full kinematic chain, but just observing it from the data. So we don't have any prior on the kinematic chain. We just look at the data. Now in this case, it's only one object, but we can actually also detect independent objects. The approach is basically you put all your subspaces here, and then you look at how at some measure that has to do. So you compute all the principal angles between every pair of subspaces. You put and then you compute some affinity based on that angle. So if the angle is if they intersect, if the subspace perfectly intersect, in that case, you'll have a 0 here. And you know that they are linked together. So in practice, of course, we didn't enforce anything like that. But so you see, basically what we do is we do a minimum spanning tree in this graph here. And that typically would correspond to obtaining the kinematic chain automatically. And of course, as you go on in the kinematic chain, if at some point you need to include an edge that is above some threshold that is too large, which means that the subspaces actually are not really intersecting, then you just stop linking things. So you stop with the kinematic chain you have, and then you look at the smallest value in the remaining graph, the disconnected graph, to look for a second body that might be articulated. And so that way you can actually build up the whole kinematic, all the different kinematic chains that are in the room. Notice that it can also work for degenerate shapes, like a door is like a 2D space, but it's also articulated. All those things can actually be dealt with by this thing. Also articulated body parts. So it's completely generic there. So I'll finish with showing you the videos. So that's the data we used. At this point, we're still limited in terms of we need to track, because we just use the standard factorization kind of things, we need to track all the features and all the views, which is a strong limitation. We have ideas on how to go beyond that. But we started by working on the basic things here. So you see there's actually not much motion here. For this leg, for example, barely moves. And so that's still sufficient to place the articulation here, which is not perfect. So you can hear the nice thing about this is you actually see the articulation. And so it's still pretty close for most of the features. And the links are completely correct. If you look at the values, we were a little lucky, but not too much. There's, I think, 2 values here that were very close. And so we almost connected the body to the left leg instead of to the hip. So we almost did the connection from the body here. So here, the body to the left leg here. Remember, this was the leg almost barely moving. That was the reason for it. But so it worked well in this case. We might have had bad luck, but if you move the leg more, then there would have been no ambiguity. The other one, Jingyu moving here. And so the segmentation of subspace stopped automatically here. And then the kinematic changes. So everything was automatic, basically, from the tracked features here. And so notice here also everything makes sense. The articulations are where you would expect them to be here. So that's okay. And so here we really want to go beyond that and really deal with complex scenes and be able to deal with. We definitely want to be able to deal with occlusions and also perspective. An easy way probably to deal with perspective is to have only assumptions of orthographic for every body part separately, every element separately, but have the whole scene be perspective. And occlusions, we have, I think, ways to, I mean, there's been many people working on factorization, dealing with occlusions and non-complete feature tracks. And we think the same things could be used in this case here. I guess that's what I talked about. And I want to also acknowledge the funding source here, NSF, DARPA, Siemens, and the Packard Foundation for the funding. And that's it.